Hello everyone, I'm Zhu from Peking University, and I'm here to introduce our latest paper, accepted by ICCV'25, Weekly Supervised Dynamic Scene Graph Generation with Temporal Enhanced Relation-Aware Knowledge Transferring. Dynamic Scene Graph Generation, termed DSGG, aims to generate scene graph for each frame of input video, where the objects represent nodes while relation denotes edges, under fully supervised manner. DSGG task requires localized scene graph for each video frame as supervision, which is very costly. Our work concentrates on the task of weekly supervised dynamic scene graph generation, termed WSDSGG, which reduces the heavy annotation burden of fully supervised DSGG by using only one unlocalized scene graph from a single frame per video for training. The conventional pipeline of existing WSDSGG methods firstly use an external object detector to detect objects, further assign them with unlocalized scene graph to construct pseudo-scene graph labels. Finally, DSGG model are trained under fully supervised manner with constructed pseudo-scene graphs. However, external object detections are suboptimal to DSGG task due to two key limitations. 1. External detectors are trained on static, object-centric images, making them ill-suited for DSGG images that contain dynamic motions. 2. External detectors are trained solely on object annotations, overlooking crucial relational information necessary for DSGG. We conduct a systematic error analysis of external detection results, find out that inaccurate object localization and missing detections are the primary problems for external detection. Then, to assess the impact of object detection and predicate prediction on DSGG performance, we conduct an evaluation using a baseline DSGG model, separately combining oracle relation or object detection as labels for training to see the performance change. We find out that substituting oracle object detections for training yields a substantial 61.9% performance boost. These findings highlight that detection quality is the bottleneck for WSDSGG performance. Then we introduce the framework. It contains two stages. In relation-aware knowledge mining stage, we produce attention maps that emphasize relevant areas for objects and their interactive relations. To integrate temporal cues, we propose an interframe attention augmentation strategy to enhance the attention maps. Then, to utilize the knowledge stored in attention maps, we propose dual stream fusion module, which contains confidence boosting module and localization refinement module to separately improve the object localization quality and remedy for missing object detection. Finally, refined detections are used to construct pseudo-scene graphs and train the DSGG model in fully supervised manner. In relation-aware knowledge mining stage, we leverage the encoder-decoder architecture to generate class-sensitive attention maps, where two parallel decoders separately use object and relation tokens to focus attention on the corresponding object and relation regions, revealing positional cues for each object instance and relational activity. Then we fuse the class-sensitive attention maps for object and relation to form ultimate class-sensitive attention maps highlighting both object and their interactive boundaries. To further handle the potential challenges of motion blur and occlusion, we propose interframe attention augmentation, making attention maps motion-aware. Specifically, we use cross-framed optical flow and previous frame to construct pseudo-attention maps for this frame, enriching attention maps with temporal cues. Then dual-stream fusion module is proposed to incorporate knowledge and attention maps to improve detection results. It comprises of localization refinement module to improve the localization quality for external object proposals, and confidence boosting module to enhance the confidence score for objects deemed to exist, thus remedying possible missing object detection. For localization refinement module, as shown in the left figure, detection results and object proposals from class-sensitive attention maps are utilized to acquire refined detection results, e.g., green one in the right bottom subfigure. Specifically, we obtain object proposals based on a threshold-based algorithm, and uses object proposal fusion algorithm weighted box fusion to fuse the proposals with external detection results, refining the localization quality. Then for confidence boosting module, we select object categories with high probability, transforming the attention maps into object proposals, which serve as complement for external detection results by highlighting salient regions with high scores of class-specific attention maps, integrating them within external detection results with weighted box fusion. Our experiments are conducted on action genome dataset, which contains 234K frame scene graphs sampled from around 10K videos. It encompasses 35 object categories and 25 predicate categories. For task and evaluation, we first evaluate our model for object detection, with average precision and average recall as metrics. Then for dynamic scene graph generation, we evaluate our model on SGDET task, which aims to detect relational object pairs and predict the relations between them, with recall at K as metric. For object detection performance, our model show improvement for both average precision and average recall, effectively enhance the external detection results. Then for WSDSGG, our model achieves sota performance, surpassing all previous methods and advanced vision language models tailored for scene understanding tasks. In oblation study, we oblate on the knowledge sources. Relation-aware knowledge, denoted by internal, enhances solely external object detection, denoted by external, on both object detection and WSDSGG tasks. Further introducing interframe attention augmentation strategy, which denoted by IOA, can further enhance performance by incorporating temporal context. Finally, we provide a visualization. Our method yields complete scene graph predictions for each video frame with accurate object localization. The code of our paper is public. For more details of our introduction, please refer to our paper and project page. Thank you.